Today I will talk about Birkhoff-Ergodic theorem. First, let x beta mu be a triple. X here is a set, beta is sigma algebra, and mu is a measure. And today we will work with in a case when measure of all space is finite. And in that case, we can take the new measure, we can normalize the measure. And that's why we will assume that measure of all space is 1, in which case it is called probability space. And also, let T be a measurable map from x to x. By measurable, we mean that the preimage of subsets of beta are in beta. And we say that it is measure preserving. I think we had this definition. T is measure preserving. Preserving if measure of preimage of any element of beta, B will be some measurable subset, measure of T to the power minus 1 of B is measure of B. Sorry?
Do we expect that T is 1-to-1?
T is 1-to-1? You mean that is bijection?
Yeah.
No, we do not expect, of course. And here are some examples. Yes, and in this case, this system will be called measure preserving system. Preserving system. And example, it's T will be x sent to 2x modulo 1. This is map on a unit circle. This is not a bijection, but measure of preimage is the same, which I think we proved in home assignment. Another example will be T alpha, which sent x to x plus alpha modulo 1. Again, on a unit circle. And today I will use some famous theorems from measure theory. First, I will use theorem which is called dominated convergence theorem, and in Russian it's called теорема Лебега о мажорированной сходимости. Dominated convergence theorem. So that Fn converge to F almost everywhere. Actually, you can say in measure. And absolute value of Fn of x, these are less or equal than J of x almost everywhere. G of, let it be phi. And if phi is, and phi is in L1. And then F is integrable, and we can change the limit and integral sign. So limit n to infinity fn d mu is integral f d mu. And now it's just a simple fact that every measurable function can be approximated by simple functions which are, for us it will be finite sums of characteristic functions. So if f from x to r is measurable, then there exists a sequence fn, and fn of I mean this is increasing sequence of simple functions. Fn will be a sum of n characteristic functions with coefficients. I will finish this statement, and such that fn converges to f pointwise. We take a measurable function, and when we can take a sequence of increasing sequence of simple functions which are finite sums of characteristic functions, such that we have pointwise convergence. Okay, and now I will use these theorems. And first proposition, which is about another characterization of measure preserving functions. Mu is preserved by t. By t, if and only if, for all f which are bounded in infinity, integral of f d mu is equal to integral of f composition with t. And moreover, we can change here L infinity to L1. Moreover, mu is preserved. I will denote it with by star. Star is true for f in L1. Yes, what about L2? I think it will be true in L2 too. We will see. Now, I think we will see from the proof. Yes. Yes, I think actually maybe we need here this function to be. Yes, we need it to be integrable. And
sorry, but is it obvious? So let us consider some function from L infinity, and suppose we know that for L infinity, is it? It's obvious only in one side. Sorry.
I think yes, we will see now. I think if these two integrals are defined, then they should be equal. So in this direction, we just take a characteristic function of so measure of t minus 1 b is equal to the integral characteristic function composition with t d mu. This is equal to integral of just characteristic function, and this is measure of b. And now, in our direction, so I wanted to say that this is true for simple functions, because if mu preserved by t, then for characteristic functions this is true, and hence by linearity for simple functions. And now we approximate f by simple functions. So fn converges to f from this theorem, and hence fn composition with t converges to f composition with t. And then f d mu is equal to, by dominated convergence theorem, yes, and L2 is a subset of L1, actually, yes? Because we have finite probability measure.
No, it is just 1 over x squared is obvious in L sub n, but it's not in
Yes, yes. So answering to your questions, L2 is a subset of L1, and hence it is true for L2. So this is a limit by dominated convergence theorem. This is a limit m to infinity integral fn composition fn d mu. Now we can take composition fn composition with t d mu, and now again this converges pointwise, and again by dominated convergence theorem this is equal to f composition t d mu. Okay. Now I will formulate what is an ergodic map definition. Measure preserving map T is called ergodic. T from x to x is called ergodic. If for all measurable sets, if we know that preimage of B is equal to B, it follows that a measure of B is 1 or 0. And proposition 2, it will be another characterization of ergodic maps. That T is ergodic if and only if for all measurable maps, if f composition with T equals f almost everywhere, it follows that f is constant. And the proof, I think, is easy. In this direction, we just take f to be.
F is constant almost everywhere, yeah?
Yes, almost everywhere.
Yeah.
Mm-hmm. So from right to left, we take f to be characteristic function, and when we get that characteristic function is constant, which means it is our set has measure 1 or 0. And in our direction, for all a and b real numbers, such set x such that f of x is in such interval is T invariant. And hence its measure is 1 or 0. And this means that f is constant. Справа налево, слева направо?
Справа налево.
Ага. Ну, мы взяли f характеристическую функцию b.
Да.
И что? И мы видим, что что такое f композиция с t? Это характеристическая функция t минус 1 от b. И характеристическая функция t минус 1 от b почти всюду равна характеристической функции b. Это значит, что ну вот, мы имеем, наверное, здесь надо написать сейчас almost everywhere тоже, да? Что?
b надо взять просто инвариант. Просто не сказано.
Надо, можно и вариант, наверное.
Ну, вы просто предположили, что, ну сказать, что...
Да, хорошо, да, действительно. Так, ну тогда в другую сторону проблему, что я говорю, что вот это инвариантно. Ну,
Очевидно.
окей, да. Окей, yes. Yeah. And now some examples.
Мы взяли произвольное f, и у нас получилось, что из того, что f от t равно f, почти все, у нас, ну, во-первых, как следует, что f это константа. Вот, мы же, кажется, можем взять такое преобразование, которое имеет местами просто два отрезочка, остальные оставлять на месте.
Ну, прообраз любого отрезка имеет меру 0 или 1. Значит, это константа все-таки функция. Если два разных значения, да.
I'm very sorry, but should we write it t raised to the minus pre-image of b is almost
Yes,
everywhere.
yes, maybe
Because
this
the second proof is not correct without this statement.
Yes, maybe that's better.
И вторая часть у нас следует просто из определения графичности.
Вот это?
Да.
Ну, вот это множество, оно t-инвариантно. Значит, его мера из 0 или 1. Okay, example we had in our home assignment T alpha. We had a problem that this is ergodic. And another example which I will discuss is again x to the x modulo 1. And here is a proof that we can take f to be in L2 and we want to show it is enough to show that that f composition with T is if so we take f2 and we assume that f composition with T almost everywhere equals f, and we want to show that f is constant. So we need to show it for characteristic functions, but actually for L2. But in L2, we have, it's a Hilbert space, so we have a basis, and f of x can be written as sum of ai exponent of 2 pi I x, Fourier expansion. And when f composition with t of x.
Maybe a sub m and 2pim x.
Yes, thank you. When composition f with t is sum of an e 2 pi I 2nx. And when hence an is equal a to n. But function is from L2. This means that sum of squares of these coefficients is less than infinity. It's finite. And this is a contradiction because we have, it's not a contradiction, it means that only a0 can be non-zero. Otherwise, it's diverges. Now I'll start to prove some ergodic theorems which say that you will see that if we apply t many times, in average, the function goes to some measure okay, let me formulate. Theorem 1, mean ergodic theorem. To some t invariant function. Mean ergodic theorem x beta mu t, it's measure preserving system. Preserving system. And new notation ut of f will be f composition with t. And so now we live in L2. And L2 is Hilbert space, and we have orthogonal projections. And let PT be an orthogonal projection to I. This is orthogonal projection onto I, and I is a set of f's such that ut of f is equal to f. And this is a closed subset, of course. And then for every f, L mu square 1 over n sum from 0 up to n minus 1 ut I f, so it's I compositions of t, converges, of course, in L mu square to PTF, to the projection. And PTF, of course, is an element of I, so it's stable in the UT.
Получается, у нас не вот, во-первых. Во-вторых, над стрелкой что написано в распределении 5?
Где? Вот здесь равно.
Нет, когда 5 определяем. То есть
PT, orthogonal projection.
It's in sense of L2.
Yes, in cells of L2. Proof. Let us define J to be a set of differences, UTF minus F. J maybe not is not maybe is not closed. And first, I will show that I is a subset of J orthogonal. Let F be in I. We want to show that it is orthogonal to J. This means that, yes, we want to compute such a scalar product. And this is equal to, we can open brackets, minus F J, and this is 0. Why it's 0? Because because F is equal to UTF. So this is UTF, UTJ. And T is measure preserving, and this means that these two integrals are equal. Okay, now in our direction, I want to prove that J orthogonal is a subset of I. If F in is J orthogonal, then when UT J minus J F is 0 because F is orthogonal to such functions. And hence UTJF is equal to JF, and this means that UT star of F is equal to F. Because we can UT change to UT star F here, and we see that such difference, scalar product with any function is 0, which means that itself it is 0. So in Hilbert spaces, if we have some operator, for example, UT, it is equal to J UT star F. And with just a definition, maybe taken as definition of UT star. And this always exists.
У нас пока что получилось, что интегралы равны. Мы получили равенство UT звездочка F с F.
Okay, we have a J UT star F minus F is equal to 0. Do you agree? And G is arbitrary. And now we just compute UT F minus F L2 norm. And here square. And we use such fact. So it will be UTF scalar product with UTF gives just F scalar product with F. So it will be 2 F square minus, and here we change UT to UT star. f ut star f minus ut star ff. And this is 0. And this, which means that f is an I. Okay, we proved that J closure of J is equal to I orthogonal.
What we suppose about f? It's just an arbitrary function.
We suppose that f is orthogonal complement of J.
Yes. F is in G orthogonal.
Yes, J orthogonal.
Можете, пожалуйста, в конце фокус еще раз объяснить, вот когда мы звездочку влево перекинули?
Ну, мы раскрываем скобки, да? Мы идти вот так можем с звездочкой перекидывать. Ну, вот мы перекинули.
Мы можем также звездочку...
Да.
То есть, если у нас
Ну, можно же менять просто все местами и сопрягать просто.
Так,
А, даже не сопрягается у нас наоборот.
так, и получается у нас... мы взяли просто сейчас, да, f и ut, да, и потом просто перекинули как раз.
Мгм.
Хорошо. А как мы получили...
Вот это?
F, не, что f в и лежит?
F, V, ну и что такое? Сейчас, вот он.
Да.
Это значит UTF равно F, а мы получили, что UTF минус F, ну, норма 0, значит оно 0.
Сейчас. Понятно.
Сейчас, подожди. Тут вопрос. Мы взяли G ортогональный. И...
Ну, мгм.
И доказали сейчас, что F лежит в I.
И доказали, что...
То есть мы доказали, что G ортогональное вложено в I.
А до этого доказали, что И вложено в G ортогонал.
Да, а теперь мы хотим G...
Значит, И равно G ортогонал. Значит, вот. Okay. And now every f is a sum of projection to I plus R, and we proved that this R is in closure of J. And now, if we take such sum for element of I, we'll get the same, because ut of f will be equal to f, and such sums will be equal to ptf. So it is enough to prove that, so we want to show that such sums for R tends to 0. So this tends to 0. Okay.
That's obvious.
That's obvious for R and J. If R and J, why this is obvious? Because J is, where is the definition here? Ut f minus f. And if we apply this operator several times, we get that so 1 over n sum of 0 n minus 1 u t I r will be 1 over n utn j minus j. Here j is the function, so r is utj minus j. G.
G малое
Yes. Let me write it here. R is ut G minus G. Because R is in J. We decided. So, so for R and J, this is easy. And now for R in closure of J, we just take.
Почему мы заменили тогда ut на ut n объясняем?
Вот здесь у нас была частичная сумма, да? А само R это была такая разность. Вот если мы будем применять ut, то у нас все посокращается, останутся только два конечных. Вот. А здесь еще одна n коэффициент. And if R is in the closure of J, then we just take a sequence. R is the limit of Ri. Now, for example, R minus Ri is less than epsilon, and for every n greater than big N, 1 over n sum for Ri is less than epsilon. So we can take such a Ri, then take n sufficiently large, and then we get that the same sum for R will be less than 2 epsilon. So it tends to infinity. Okay? Yes, we proved for J. Now we prove for let R be in a closure of J. R is a limit of some elements of J, and we take Ri close to R, and
Как мы взяли, во-первых, почему это выражение можно сказать, что оно валидное?
ну, выбрали Ri сначала, меньше эпсилон. Потом выбрали достаточно большой n, что все такие частичные суммы меньше эпсилон. И теперь, ну, берем там разности, и получается меньше 2 эпсилон. Okay. And this is for all n greater than big N. This is less than 2 epsilon, but epsilon is arbitrarily small. So this goes to 0. Okay, now L2 is the subset of L1. And so let us prove such theorem for L1 now. But we will use our theorem for L2.
Yes.
This will be corollary. So again, we have measure preserving system, and for all f in L1, let us give a notation. ANF will be with partial sums, 1 over n, sum ft, ft. Okay, then for all f, ANF tends to some function in L1, and f is T invariant. And proof.
Утверждение, значит, что если
Да, вот мы в прошлой теореме для L2 доказывали, и здесь было вполне конкретно, ну, проекция была, да, на это пространство. А здесь вот, ну, какой-то f, но она t-инвариантная. Proof is like that. Let's take G in L infinity. L infinity is a subset of L2, which is a subset of L1. When an G subnorm is less than norm of G. Okay? And hence, for B in beta, such scalar product Fn Ang B is less than G infinity measure of B. And Ang, we know that in L2 it tends to some G bar. And hence, G bar multiplied by characteristic function of B is less than G infinity mu B. And hence, G bar is in L infinity, so it's bounded. And so we started with G. After that, we applied our theorem for L2, and we get G bar, and now we just say that it is bounded also, as was G. And it is bounded, and this means, in particularly that Ang tends to G bar not only in L2, but also in L1. Okay? So we proved our theorem for bounded functions. And now we prove for every function f is in L1, G is L infinity, and f minus G, L1 norm is less than epsilon. Yes?
Как мы доказали, что f с крышкой
Ну, мы сейчас для всех докажем, на самом деле. Мы сейчас, okay, so we take G close to F in L1 norm, and this means that An F minus An G in L1 norm is less than epsilon. But also that means that G bar minus Ang in one norm is less than epsilon because this sequence converges in L1 norm. And so we see that Ang is we can get that Anf minus Amf L1 norm is less than 4 epsilon for Nm sufficiently large. Yes, because Anf is close to Ang, this is close to Amg, and these two are close to G bar in L1 norm. Hence, this is a Cauchy sequence in L1, and this is a Banach space, and hence Anf is Cauchy sequence, and it converges to some f bar in L1. And now we show that f bar is T invariant, but this follows from the fact that we see that AN F composition with T minus AN F, this tends to 0 in L1 norm. Yes, again, because we have such telescopic function sum, and all terms cancels except first and last. And this tends to F, this tends to F bar, this tends to F bar. Okay, now I will start to prove the main Birkhoff-Ergodic theorem, which has the same meaning, but now we want to understand something about almost everywhere convergence. For this, I will need some notation. So let me fix AKF was. We know that it's such sum. F n star will be supremum of 1 k n AKF. F star without our indexes is just supremum of over all k and A bar is limit superior of AK. Now theorem, this is theorem 2. Let lambda be a T invariant. I remind that this means lambda composition of T is lambda almost everywhere. Function on X, and lambda plus, it's such notation that each function, it can be decomposed as f plus minus f minus. Here, f plus of x is f of x if f of x is greater than 0 and 0 otherwise. And f minus is the same. Okay, and lambda plus is in L1, f is also in L1, and T is measure preserving. And then integral over such set f star greater than lambda, f minus lambda is greater than 0. See, f star is a supremum, and on such set f may be less than lambda, but on average we see that it is greater than lambda. And I will note that if lambda is constant, this is called maximal ergodic theorem. ergodic theorem. And this is a generalization which I took from 2006 article by Michael Kian and Carl Peterson. So this is slight generalization, but it makes things much easier. So let us start to prove. So first we may assume that lambda is in L1 of such set, star greater than lambda. Because otherwise, lambda is bounded by f, and if it's not in L1, it's so this integral would be plus infinity. Let me denote this integral I. I is infinity.
Sorry, why it's infinity? We integrate on some set where why it can be minus infinity, for instance. We suppose that f minus lambda.
Ну, f со звездочкой больше лямбда же, да, она ограничена вот так.
Не, ну f со звездочкой это больше f.
В
Получается,
смысле, что она тоже не из L1. Okay, actually I think we may assume that lambda is in L1. It will be enough. Okay, let's maybe think about this a bit later. Okay, so you say that lambda may be like f star, and f star can be not in L1, yes? Okay, let me continue. Just okay, we will return to this question at the end. Okay, if lambda is in L1, then it is in L1 of x, because if f star is less than lambda, less or equal, so on this set, f is less than lambda, because this is supreme. And so lambda minus.
Можете начало просто не прочитать вот из строки последней самой, потому что не очень понятно, что написано.
I want to show that lambda is an L1, actually. So we know that it is here. Yes, we have some problem. We're not sure, but okay, let's assume it's here. When I want to prove that it's in L1, why? Because on the complement set, on this set, f is less than lambda. And this means that lambda minus is less than minus f plus lambda plus. And this function is integrable. So lambda minus is integrable. Okay. Maybe if lambda is very positive, yes, it means lambda plus is not in yes?
Сейчас. If lambda plus, sorry, it's always because lambda plus is in L sub L in
Yes.
L1 and
So
minus giving us only positive.
yes, yes. So it's if the integral diverges, it must diverge to plus infinity.
Sorry.
Okay. So now everything is fine, and so assume that first we will prove this theorem for f in L infinity. Assume. And let En be such that Fn star greater than lambda. When f minus lambda characteristic function of En is greater than f minus lambda. Why? If x is not in En, what does it mean? It means that Fn star is less than lambda, and in particular f minus lambda is less than 0. Okay, and now we want to look at our sequence A. So let us.
Извиняюсь, такой вопрос. Почему у нас f минус лямбда на как раз таки en больше брать, чем...
Ну, на E она не совпадает, а на дополнение f минус лямбда отрицательная.
Все, да, понятно.
Ну, не положительная.
Да-да-да.
Ага. Now let us analyze our sequence TIX. So we want to look at f minus lambda characteristic function of En. So we apply f minus lambda characteristic function chi En to our sequence. So we apply our function, yes, to these terms. And so we start with x. After that, our TIX is not in En for some time, maybe for some time. After that, we arrive to En, yes? And let k be the first number such that TKX k minimum number such that TKX is in En.
То есть, получается, у нас все еще, то есть у нас везде en берется.
Сейчас мы N зафиксировали, да.
Да, то есть, там хет en это, или это хет, как вот еще, просто индекс вычислить.
То есть мы
Чьи
можем-
N то это?
То есть мы можем считать, что у нас единички счет идет на самом деле.
Сейчас. Нет, сначала у нас не попадало в EN,
Ну вот,
и у нас здесь были нули, да. А вот K первая, которая встретилась. So this is greater or equal when f minus lambda apply to TKX plus maybe it's not very good notation. I mean here plus we apply with operator to each term, and then we take sum, okay? So now L is arbitrary number, but then I will say what we want from it. This is equal to L, A, L, F, Tk, X minus lambda applied to Tk X. Okay, lambda is T invariant because L times ALF average, yes, TKX, L average, minus lambda applied to TKX. Lambda is T invariant, that's why.
Yes. It's obvious.
Just a second. Okay. And we know that TKX is in En. What does it mean? En is such set that some partial sums are greater than lambda. So we can take L, there exists L not greater than N, such that this is greater or equal than 0. Okay? This is the main step. TKX is in En. Ну, TKX, оно в En, а En это по определению вот такое множество, что Fn со звездочкой больше лямбда. То есть кто-то из частичных сумм, кто-то из вот этих частичных сумм больше лямбда. Ну вот L как раз мы берем. So we can take L such that this is greater or equal than 0.
Но это должно быть для иксов, принадлежащих En.
TKX is in N. We apply this to TKX. And then we get some partial sum which is positive. And when we apply the same analysis, we take Tk plus L, X, maybe it's not in En, but when this is 0, when we apply T, when we first arrive to En, and again we take such sum. And but at the end, maybe we can take L, but all K plus L minus 1 will be greater than big N. So I want to tell that for all N sufficiently large, there exists J such that J is close to M, and also K such sum F minus lambda chi En of TKX is greater than sum from J up to M minus 1 F minus lambda chi En TKX. And this is greater than minus big N subnorm of F plus lambda plus of X.
Minus N.
Here we have no more than big N's summons. f gives each summon gives no more than of infinity norm plus value at x.
Это откуда мы знаем?
Потому что вот здесь не больше, чем n большой слагаемых.
Не больше. Почему здесь m?
Нет, m очень большое число. Да?
Да.
Дальше мы вот это все применяли и отделяли положительные куски.
У нас G где-то такое, чтобы туда.
G это последний раз, когда мы, например, попали в EN, а дальше вылезли за пределы m маленького.
Еще раз. То есть у нас тут не больше n слагаемых, то есть почему такая оценка вторая n? Откуда первую взять? Почему?
Вот это?
Не.
Вот это?
Нет, посередине.
Вот это.
Да.
Еще раз, мы вот делали вот этот процесс.
Да.
Отделяли положительные куски. Мы так делали, пока у нас вот в этом моменте, вот здесь вот не вылезло вот это k плюс l минус 1 не стало больше m. Вот эта длина не больше n большого.
Не больше. Сейчас. То есть мы разбили.
Угу.
У нас есть какая-то длинная сумма, вообще говоря.
Да.
Мы можем разбить.
Мы выделили положительные слагаемые, да, выделяли.
Мы можем выделить. Что у нас случилось? Мы предположили, что k это первый момент, когда мы попали в EN, так?
Да, до этого нули.
Если вот мы после этого шага как раз таки из EN вышли?
Ничего, у нас всегда вот мы шли до момента, когда у нас там оставалось n. Вот делали вот этот процесс.
Нет, еще раз. Это только наш курс. Мы попадаем в тот момент, и пускай у нас как раз таки на l-ном шаге tk плюс l от x уже не лежит в EN.
Нет, не проблема, если оно не лежит в EN. Нет, здесь мы ничего не говорим, мы только tk от x знаем, что лежит в EN.
Нет, хорошо, мы взяли этот кусок, мы его оценили, что он больше нуля.
Дальше продолжаем. Если не в EN, у нас нули. И дальше идем. Попали первый раз в EN, применили. Может быть такое, что вот мы применили, а вот это уже просто сумма наша вылезла за пределы нашей суммы. Что вот этот момент,
понял. То есть у нас осталось.
Угу. And now we just integrate with respect to x and divide by m. Okay. So what we get with m integral of En f minus lambda is greater than minus n f sub norm plus lambda plus 1. And now we divide by m and let m tend to infinity. This means that such integral is 0. That it is greater or equal to 0. And now, by dominated convergence theorem, integral over star greater than lambda, f minus lambda is greater or equal to 0. So we proved our theorem for f in L infinity. And for others, we just approximate. Phi s will be f absolute value of f less than s. Phi s almost every converge to f. And in L1. Yes. Отрезали, просто смотрим, где модуль f не превосходит s. Берем, а остальных 0. Вот. And also, for fixed n phi s n star converges to fn star also almost everywhere and in L1. And finally, measure of phi s n star greater than lambda, symmetric difference with fn star greater than lambda, this tends to 0.
Звездочка или плюсик?
Where? Here is star star. Everywhere. Okay, and now we just see that 0 is greater than integral of phi s star n greater than lambda. Да. Phi s minus lambda. And by the dominated convergence theorem, this tends to integral fn star greater lambda f minus lambda. And again, we let n tends to infinity. And again, by dominated convergence theorem, we get our theorem. And now I will prove Birkhoff-Ergodic theorem. Ой, зря я стер. Ну ладно. Окей.
Сейчас вот последнюю строчку не стирайте, пожалуйста.
Окей.
Вот с интегралом.
Okay, I will write. Oh, sorry. Yes, this theorem. Let me write briefly once again. We have f star greater than lambda, f minus lambda greater than 0. Yes, if lambda is t invariant, etc. Now, our main theorem, theorem 3. Birkhoff-Ergodic theorem. Ergodic theorem. Again, we have our space, measure preserving system. And for any f in L1, AKF almost everywhere converges to F bar. F bar in L mu 1, T invariant, integral F d mu is equal to the integral F bar d mu. And if T is ergodic, then T, что? Вот здесь? А можно стереть, да?
Да.
Ага.
Получается, после крыши текущее лем, оно Т-инвариантное?
Т-инвариант, да. If T is ergodic, we can say even more that F d mu is equal to F bar almost everywhere. But this is okay. It's easy. And now the proof will be rather short. Proof. So plan is like that. We show that integral of a bar is less than integral of f. I will denote with a bar is limit superior of AKF. Okay. Then why the theorem follows immediately from this? Because when we can apply the same for limit inferior AKF, and we will have that such integral is less than minus f, and hence such difference, such integral is less than 0.
That minus integral of a over line is less than minus integral of f.
Что?
Откуда второе?
Второе, применили к минус f то же самое. И вот это заменить, ну, они поменялись. This means that lim sup equal lim inf almost everywhere, and that just means that AKF converges almost everywhere to f bar, which is, for example, lim sup. Also, we know that AKF converges to some L1 function in L1, but then it must be this function because convergence in L1 implies convergence in measure, and hence some subsequence converges almost everywhere, and then they are the same. F-bar, ну вот, например, такое можно взять. This is in L1, 2, and the integral f d mu hence equal to integral ak f d mu equals to f bar d mu. And f is t invariant because we proved it in the corollary, and for ergodic is just constant because every t invariant for ergodic system it should for ergodic function such f should be constant. Okay, now we just prove the final that, and that's easy because our theorem. So first, so we want to prove that integral a bar less than f. We consider f plus and a bar of f plus. It just was same limit superior. And for all lambda less than a bar, we have of f plus. We have we set f plus star greater than lambda is equal to x, to a whole space. And hence f integral of f plus is greater than integral of lambda, and which we can make to converge to our a bar f plus.
Еще раз, x это все пространство или?
X это все пространство, да.
Почему еще раз у нас такое?
Ну, потому что оно меньше лим-супа. Если оно меньше лим-супа, ну, вот у нас как раз f. Стар это вообще супрем по всем. Okay, so a bar plus is less than a bar of f plus, and hence this is integrable. Hence a bar is integrable because we can apply the same for a minus, and
f plus больше, чем интеграл от лямбда, это мы имеем потому что это вот тут мы воспользовались максимальной логической теоремой.
Да.
А потом что у тебя написано просто? Вот после f, интеграл от f плюс больше, чем интеграл от лямбда.
Ну, а это можно устремить.
Сейчас, как это мы устремляем?
Ну, так понимаю, минус эпсилон просто берем.
Я не понял, где минус эпсилон? Почему у нас вот f плюс больше интеграл от лямбда? А дальше что написано? Что мы к чему устремляем?
Лямбда вот здесь устремляем.
А почему мы можем сколь угодно первыми интегралами приблизиться к
Берем минус эпсилон. У нас берем вот это бар минус эпсилон.
А почему оно существует? Мы же не доказывали, что бар от f плюс, оно вообще как-то, может быть, это там бесконечность.
Ну, ой, сейчас, ну... Ну, сейчас. Бар от f плюс бесконечность. Сейчас, ну вот мы какую бы лямбда ни брали меньше абара, мы никогда не получим больше константы фиксированной. Мне кажется, это значит, что абар не может там...
Сейчас, подожди. У нас вообще, смотри, мы доказали, что интеграл от f плюс больше, чем лямбда. Да? Во-первых, почему от f плюса будет первым интегралом?
Что еще раз?
Почему от f плюса будет первым интегралом?
Сейчас. Смотри, для любой лямбды, не происходящей от s плюсом, интеграл по такому не происходит какой-то фиксированной константы. Тогда вот этот интеграл, но если он расходится, но мы можем чуть-чуть уменьшить, чтобы до сих пор, ну, все еще расходилось.
Сейчас. А для любого... мы можем
Ну,
чуть-чуть...
ну, чуть-чуть уменьшить, чтобы сходилось, но было большое.
Сейчас,
Ну,
почему это будет первым интегралом?
что?
Вот мы в этой логике существенно...
Вот это?
Да.
Нет, несущественно. Еще раз, если он расходится, мы можем взять функцию поменьше.
А почему она будет первым интегралом? Ты сказал вычту эпсилон.
Ну, не вычту эпсилон, я сделаю еще, ну, меньше сделаю еще.
Ну, а вдруг там между ними какой-то скачок? Ну, это же неправда, я же могу взять просто лямбда равны единичке. Ну, это логика подходит. Вдруг между единичкой какой-нибудь функции вида 1 на x ничего просто промежуточного.
Ну, возьму ее равной вот этому на, если не превосходит значение функции n большого, а настоящее 0.
А почему она будет первым интегралом?
Что, почему сходиться будет?
Нет, почему вот эта функция, предположим, да, ты взял там ограниченное какое-то множество, почему это множество будет, ну, почему эта функция будет t-инвариант? Ведь чтобы работать логарифмическая теорема, нужна t-инвариант.
Плюс. Сейчас, ну, мне кажется, значения у меня со звездочкой от f плюс, они, вот она инвариантна. Потому что это вот эти окаты, если я применяю f, они почти не меняются. T, если применяю t. Смотрите, АКФ, это там сумма большой, если я t к нему применяю, оно очень мало меняется. Поэтому липсуп, он тем более t-инвариантный. Окей?
Так, мы берем от от f плюса. Можно, да, вот действительно, можно просто срезками.
Да, срез. Ну все, да. И теперь просто берем лямбда там равное. Now we take star minus epsilon and we get that f is greater than lambda and this converges to such integral and hence we proved our 2 star.
Еще раз, почему мы доказали пока только что интеграл от x плюса больше, чем интеграл от от x плюс?
Мы доказали, что вот это не ограничено. Просто мы сказали, значит, а-бар интегрируемо, да? А теперь мы то же самое для а-бар делаем, там вычитаем эпсилон, лямбда такой берем. Вот так. Опять же, по той же теореме. А это можем устремить, чтобы сходилось к
Вы
А бар.
сказали, что А бар интегрируем.
Да. Теперь берем лямбда А бар минус эпсилон. Применяем нашу теорему, там на множество все x будет. И теперь лямбда, ну, эпсилон стремляем к нулю, и получаем нужное неравенство.
А почему F, а не F? А, ну ладно.
Ну вот. Окей, do you have questions? I think I finished here.
Скажи, а нам же... А, нам это и надо было.
Мгм.
Huge talk on homogeneous dynamics. Let's make 10 minutes break. Спасибо большое за хороший доклад. Okay, so thank you once again for a very nice presentation. Now we feel very knowledgeable in ergodic theory and some basic aspects of it at least. And so we switch to our next huge block. You selected homogeneous dynamics. So today's lecture you can consider as a kind of a teaser for the further study, and it will take us a few lectures. So what does it mean, the homogeneous dynamics? It means that we consider the dynamics on a homogeneous space. So I will proceed in the Google Classroom. Today I will upload the books and the articles that I consider useful in this context. So my presentation will be rather informal, and all the technical details can be recovered using the materials that I will leave there. So what does it mean to consider a homogeneous space? It means that you take a Lie group and you consider its quotient on a lattice. And we already had this notion, the lattice, and I recall you that it's a discrete subgroup. Such that a fundamental domain F gamma of the left gamma action on G has a finite left Haar measure. So I proceed with some examples. Wait a few seconds because I need probably to tell you what does it mean to have a dynamics. So we have a kind of map. You take an element from G and you consider the map defined on X to X, where every point goes to its image under Ft, where this one is one parameter subgroup of G. Then T can be different. You can consider either discrete or continuous dynamics. It's up to you. So this is one parameter subgroup of G. And T can go either through natural numbers or it can be all positive real numbers. It depends. Either you're interested in a discrete or continuous case. So your natural question should be, can we provide any examples of these lattices, discrete subgroups? Do we know already some examples of homogeneous spaces? Or maybe it's something very artificial, or maybe it's something very complicated. And the answer is that in reality you know plenty of examples. And we already studied some aspects of dynamics in homogeneous spaces. So the classical example that you can keep in mind, maybe one example, is that you start with R. It's abelian additive group of translations. And you, as a lattice, you take integer translations. And then you consider X, which is a result of the factorization. So since all the groups are abelian groups, there is no difference to consider the left or the right action. So it's a torus that you are used to know since many years probably. And of course we know that we are equipped with a Haar measure in this case. And this Haar measure is simply dx. It's the same thing as the Lebesgue measure. And as a natural map that you can associate with it, you can consider just a translation on some angle alpha. So there is a very classical theorem that probably all of you already met at some occasion, which is attributed to Weil, but then there are also alternative proofs by Sierpinski and Boll. And the theorem is the following. So it's not the theorem of homogeneous dynamics in a classical sense. It's just something very standard that people know in number theory and in dynamics. And it's about equidistribution. So L. And it works as follows. We consider alpha, Bohl, B-O-H-L, like that. So we consider some irrational alpha. And then we consider whatever f, which is a continuous function defined on our favorite homogeneous space. It acts from T to R. And then we say that the lim, when n goes to infinity, of 1 over n, sum of f and alpha, is equal to the integral on T of f dx. So it's a little bit similar with what we discussed on the first half of our lecture today. But now I want to attract your attention to the following fact, that this theorem is relatively simple, and it admits two different types of proofs. One proof is what people usually do with it, and it relies on some harmonic analysis. It's a kind of explanation for number theorists why do they need to study Fourier transformations at the second year of analysis in our course. So the idea is the proof number one. I'm not going to cover all the technical details, it's just a sketch, but the idea is that it's based on a kind of harmonic analysis. And you can take Weierstrass approximation theorem, which claims that trigonometric polynomials are dense in the set of continuous functions on T. And so by this theorem, it's enough to show that the similar statement holds for finite Fourier series, so that we have f and alpha equal to the integral T fx dx. This should hold for finite Fourier series f of the form f of x but we want alpha to be irrational. Yeah, because otherwise we don't want to think about this periodic orbits. So in order to establish this star equality, it's enough to check what's going on when we consider this equality by coefficients. So first we check that lim 1 over n of the sum of C0 is equal to C0, so it's exactly the integral of fx dx. So this is the first observation we make. And the second observation is that for k, which is not 0, if we consider this limit, 1 over n of the sum of e, so this should go here. Maybe I will rewrite it. Sorry, I will rewrite it here, otherwise there is not enough space. So I take the limit, 1 over n of the sum from 1 to n e 2 pi k n alpha. So this I can rewrite as a limit e 2 pi k alpha n, and still goes to infinity, on 1 minus 2 pi k n alpha, 1 minus e 2 pi k alpha. So this just follows from the formula for the sum of the geometric series, naturally. And here it's important that alpha is not rational, because otherwise you can get 0 here and you are kind of in troubles. So we use here that alpha is irrational. And combining these two observations, we arrive to this harmonic analysis style proof of the statement. But today I want to, this probably you saw already as a part of your calculus classes. But today I want to advertise to you another way of proving the same fact, which is called on which is based on so-called measure rigidity argument, because then we will try to generalize this argument and will rely on it in a much more general context. So an alternative proof of a similar fact is so-called measure rigidity. So what does it mean? We consider the following map from f to nu n of f, where nu n of f is defined as the sum normalized over n of f and alpha. And I claim that this provides us a Borel probability measure on T. So it's easy to see that our T is compact. But then, if it's compact, then we get a series. Of course, you understand, for each n, you get your own measure, so you get in reality a series of measures. And this sequence will be relatively compact.
But how do you define measure? Do you want its measure on space of all or what? On T?
So let us say just that we define nu n in the following way. It's not important right now if it's a measure or not. We just associate with each n capital the following sum. Then you get a sequence like that. And so you can claim that since it's compact, this is a relatively compact. And to be relatively compact means that every subsequence contains a convergent sequence in weak star topology. So maybe we should close it up. Ну, в точности это означает, что она содержит сходящуюся подпоследовательность. Сейчас как будет relatively compact по-русски, что-то меня тоже клинит. Относительно компактно, наверное, так и будет. Я не знаю, может быть, это как-то устоявшееся называется по-другому. Значит, теперь, so we proceed, we say that this is relatively compact, and thus, how we will construct this measure? So first we construct this map, and then we say that since it's relatively compact, we know that every subsequence in weak star topology contains a convergence sequence.
Все-таки можно вопрос, что значит DN? Оно предкомпактно называется.
Да, наверное.
А что значит DN? В каком смысле? В каком пространстве?
Это не D, это new.
New
Нет.
N.
Ну вот пока вы не сказали про меру, мы сейчас скажем, почему это мера. Пока мы просто определили вот такое пространство. Вот мы по каждому f будем считать вот такие суммы. У нас тогда получается последовательность этих new n отображений. Значит, из них можно выделить будет сходящуюся под последовательность.
Мы рассматриваем пространство
Ну, у вас функции определенные на множестве функций.
то есть у нас это линейный оператор на множестве непрерывных, скажем, функций.
Ну, у вас есть, да, просто оператор на множестве функций, и вы, соответственно, по нему определяете такую, у вас даже не один, а последовательность этих операторов, и вы говорите, что так как ваша функция была непрерывной на компакте, то f у вас же мы договорились, что она непрерывна на компакте.
New N предкомпактно, то есть это критерий предкомпактности в C, но тут же у нас получается банк, то есть линейный оператор на C.
Но это можно проверить, это упражнение убедиться в этом, но оно несложно. Давайте мы сейчас построим, и будет понятнее. Просто я напишу, что это значит для конкретного отображения. So we define T alpha, which is the rotation, x goes to x plus alpha. And, okay, here I forgot to say that then this subsequence went to this nu. So I claim that this nu is invariant with respect to T alpha. And for each f which is continuous on our torus, nu n of f composition with T alpha, which is 1 over n, the sum of n plus 1 alpha. It's nothing else than 1 over n f n alpha, sum from 1 to n, plus 1 over n f at n plus 1 alpha minus 1 over n f alpha. And we see that the correction on this T alpha becomes very small. So if we knew that there is this convergence statement, then we can also expect that nu ng of f composition with T alpha will converge as well to nu of f. And since the composition of f and T alpha belongs to the set of continuous function as well, then we have no doubts that this nu ng f T alpha should go to the nu f T alpha, because we had this convergence on all the continuous functions. And so this means that these two guys are basically the same people for any f. And therefore, we know that nu should be invariant with respect to T alpha. So we know that since it's T alpha invariant, then we also know that it should be invariant under the cyclic. So it is invariant under all the degrees of T alpha. So under the action of the cyclic group given by T alpha. And since we know that, okay, maybe I should make a break here to make it clear what I mean. So the idea now is that we want to prove the same statement, but using some measure-based arguments. So we constructed this new n for each f. We constructed such a functional new n. So this new n is defined on the set of continuous functions on T. And then we say that by some standard arguments from functional analysis, one can see that if this one is compact, this, which is on the dual space, should be relatively compact, and then it should converge to some nu. Now I claim that this nu, due to the definition, is necessarily T alpha invariant, where T alpha is the translation on our circle on T. Why it should be true? Because on the one hand, we take some continuous function and we apply this. We say we write by definition what it means to consider nu n on Fn composition with T alpha. If it's a composition with T alpha, we should write this F T alpha here, F composition T alpha. But what is the composition of T alpha? You just should add alpha to the argument. So you should replace Fn alpha by Fn plus 1 alpha, right? So that's what we did here. Now we split it into two different parts. First part led us, so here you had to sum up once again from n1 to n. So first you consider Fn alpha, and then you consider their difference, right? So you get everything as you expected here. This is nothing else but the definition of nu n of f. And here what you have is the difference between n plus 1 alpha just from one capital N, because all the people before they used to coincide, and then you should remove also 1 over n of f alpha from here. So if you look here and you lead your n capital to infinity, then you will see that this guy provides you very little correction. And so this correction becomes very small and does not change much. So you can expect that these two people should just coincide, because this guy goes to infinity, goes to 0. You have n in the denominator all the time here, and f of alpha is a constant, right? So it will go to 0. So you have this convergence. But at the same time, you could not think more about this T alpha as it is. Here we used who is exactly T alpha. But at the same time, you could just apply the definition. We defined it on all the continuous functions. So this is also a continuous function. And then we can just apply it in the same way here and have a subsequence that goes to this limit. But therefore, it means that this nu and this nu are just the same people. So if we added the correction on T alpha, it did not change anything. And so we had this property of invariance with respect to T alpha. So then we could say that it's also invariant with respect to all the degrees of T alpha, because, okay, if you had the invariance with respect to T alpha, then you consider T alpha square, you apply the same logic, you get the same statement, right? So, but then we have not used yet the fact that our alpha is irrational. Here it was important for us at that moment, but in the second proof we have not yet applied it, and it's the moment where we will do it. So alpha is not a rational number. What does it mean for us? Then we know that for any y in T, there exists a set of integers n I such that n I alpha converges to y, modulus 1, because we live at the circle. So morally, what does it mean? We just use the fact that the the rotations on the rational angle are dense in the set of all rotations. So then you can say that it implies the fact that if our nu was invariant with respect to T alpha and all its degrees, then you can get any translation, and our nu would be invariant with respect to any translations, because any other translation can be approximated by those. So under all the translations. But then there are not many probability measures that are invariant under the whole group. So we know, due to this fact, that nu should necessarily be the Lebesgue measure. And in other words, that this should hold. So this limit nu is unique. Thus limit is unique. You remember, because there we consider the subsequences, but for each subsequence we can show that it's a Lebesgue measure. So all of them should have the same measures, and thus we have the convergence for the whole sequence, not for the subsequences. And this convergence leads us exactly to the statement of the theorem.
Sorry, question. Why we can approximate every rotation of circle by rotation and I asked it because we can approximate only one point, but
you can approximate this thing by itself, and then you can check that it will give you the approximation for the maps. So this is not kind of absolutely automatic. As I said, I provide not the proof, but the sketch of the proof.
One question: if Ni does depend on, sorry, it means that.
So you consider the rotation on some other angle beta, and then you approximate beta itself by the sequence of this Ni alpha. And so then when you consider the rotation, you consider x plus beta, instead of x plus beta, you consider it x plus Ni alpha, and that's what you do. Да, у вас получилась мера вероятно относительно любых поворотов, но такая мера только одна, это мера Lebesgue. Вот. И so what is the idea of the argument of measure rigidity? The idea is that we consider all the invariant ergodic measures, and they are not abundant. Each such measure has some strong algebraic structure. So you combine the idea of unique ergodicity, so the fact when you have just one ergodic measure in reality up to some equivalence, and you combine it with the fact that then your measure necessarily has some clear algebraic structure. Значит, давайте я по-русски еще скажу, чтобы было совсем понятно. В чем идея того, что мы делаем? Значит, еще раз, я не претендую, что мы выписали очень аккуратно, это просто скетчи, доказательства, наброски, чтобы вы поняли разницу подходов. Есть простое утверждение, можно гармоническим анализом, а можно перевести все это на язык мер. И что мы на самом деле сделали? Мы начали с того, что мы обсуждали, что вот у нас есть такая мера, она инвариантна относительно T-альфа. После этого мы проверили, что раз она инвариантна относительно T-альфа, она должна быть инвариантна относительно всех поворотов. А вот уже это очень сильное требование, поэтому оно по сути означает, что она есть мера Lebesgue. И тогда, так как она строилась как предел этих самых μn, получается, что они все должны сходиться к мере Lebesgue. Вот что такое measure rigidity? Ну, то есть жесткость мер. В каком смысле жесткость? Это означает, что вы пытаетесь найти инвариантные меры для какой-то динамической системы. И при определенных условиях у вас получается, что все инвариантные меры, вы не знаете, какие они, вы, возможно, вообще не умеете их строить. Но вы понимаете, что из-за ограничений на исходную систему при некоторых обстоятельствах ваши меры должны обладать очень понятной алгебраической структурой. И должны, соответственно, жить на каких-то, иметь в качестве носителя какие-то понятные множества, и сами формировать множество, у которого вы хорошо понимаете соответствующую алгебру. И тогда у вас часто получается либо, что такая мера вообще единственна, это то, что здесь написано про строгую эргодичность, либо, по крайней мере, даже если она не единственна, у вас получается очень четкая возможность охарактеризовать их класс и для всех мер этого класса доказывать те или иные свойства. В чем принципиальное отличие всего того, что будет происходить в этой части от эргодической теоремы? Очень хорошо, что Петр делал доклад сегодня. Когда мы с вами имели дело с эргодической теорией, мы все время говорили, что у нас все утверждения выполнены почти всегда. Вот почти всегда у нас была сходимость. Почти для всех точек мы вот знали, там, как будет устроена мера. Здесь вы увидите, что сила наша состоит в том, что какие-то алгебраические свойства мы будем способны указать для всех точек. И это глубокая и принципиальная разница, которая дает нам возможность решать очень многие задачи, которые эргодическая теория привести нас не может. So, let me provide you, I hope that the idea of this measure rigidity argument is relatively clear, in a sense, what we try to do. Now, of course, it was a kind of a baby example, so we don't know how many applications we may have if we try to do it for some abstract homogeneous space. So I want to provide you more examples of homogeneous spaces, since we are supposed to live with them for the next several weeks at least. So another homogeneous space that you already know, it will be taken from the statements that we proved in the first part of our course. Because you remember that we spend our life studying SL2R matrices. So let me generalize it a little bit and consider SL and R. This will be my group G. And as you remember, probably, we already discussed the fact that there is a particular subgroup in SL2R, which was SL2Z. You remember, we discussed it a lot. So I will consider its n-dimensional version. Right now, it's not clear that this group is a lattice, because it's not hard to check that it's discrete. Maybe you remember how we did it in the case of SL2Z. But this part about volume is not trivial. So this was proved by Minkowski, why the volume is finite. In dimension 2, which is always in your mind because it's the most explicit construction, it comes from the fact that you remember we discussed that the area of the corresponding surface, hyperbolic surface, is finite. So that's what you consider here. And now this is the example of the homogeneous space. The question now is how to run a dynamics on it. And the first option that you can consider is the following one-dimensional subgroup given by E lambda 1 t, E lambda n t. And this you already remember probably, the sum of lambda I is equal to 0. This you already remember because something relatively similar already appeared. And another thing that can be considered is the set of unipotent matrices. It's a unipotent group 1 AT 0 1 when t takes all the real values and A is some fixed matrix. So this is supposed to build a kind of a bridge in your head that you can consider what we already did when we studied geodesic flow in the context of the homogeneous dynamics. And I provided was one of the possible presentation topics that was, I think you took it, yes, the horocycle flow. So it will be also very related to what we are doing now. Even if the first glance you do something completely, much more geometrical, but in reality it's very related. So now let me advertise you a little bit how people apply the homogeneous dynamics. Hopefully you got the general idea of what we are going to do. We will study the dynamics in these kind of spaces, and you saw that they exist. Some of them are trivial, some of them are not. So now what they achieved when they used the techniques that we will study in the next weeks. And I will speak about some spectacular applications. And the first and maybe the most famous one is the Margulis proof of the Oppenheim conjecture. So let us forget for a moment about all these measures and other complicated business, and we will concentrate on the quadratic forms. Does everybody remember what is it from the course of linear algebra? So we consider Q on x1, xn, and it's just the sum of QEG, xi, xg. This is a quadratic form. And maybe you also remember that these quadratic forms, they may have different signatures. So it's when you put it in the canonic form, you remember you can see it as a sum of some squares, and some go with the plus and some go with minus, and the amount of pluses and minuses leads us to the signature as an invariant of this quadratic form. So it has both positive. Assume that our signature is PQ and that the form is indefinite in a sense that it's not, the signs are different. So P and Q are both non-trivial. We have both positive and negative eigenvalues and non-zero eigenvalues. So we will say that Q is irrational if QIG as a matrix is not proportional to the matrix with rational coefficient. So what Margulis did is his theorem from 1987. So we say that if Q is irrational, and indefinite with n greater or equal to 3, then it's separated from 0 in the following sense, that the infimum of Q applied to non-zero integer vectors, so it's not separated, so this is 0. So how it's related to the Oppenheim conjecture? Oppenheim conjecture is the following thing. It's from 1928, so you can see that it took people a while to understand what to do with it. So he considered the same statement, but he did it experimentally, so he started from n greater or equal to 5. So in reality, the fact that Q should be irrational is important only in dimensions 3 and 4. This is the first remark. just technically. And the second point is that for n equal to 2, it simply does not hold, and you don't need to be Margulis to see it. So you can take as a counterexample the following form. Try to play with it. You will see it. It's x1 square minus 1 plus square root of 3 square x2 square. And you will see that then it will be simply not true. So you look at it. Maybe if you are familiar a little bit with history, you can believe that it was teasing and important, because people wanted to prove it for a while, but only number theorists work on it, because it looks like a typical problem from a number theory. And the natural question is to ask, where is dynamics here? Some quadratic forms, apply somewhere, they give you some numbers. Why do dynamics care? And the genius of Margulis was exactly to notice where is the connection. So that's the following things that he observed. I'm not going to prove once again, we are not ready yet to do it, we know nothing in homogeneous dynamics yet, but I will try to explain you why these things are related. So,
sorry, Oppenheim conjecture is that this form is dense, that the value of this form is dense, or
it's the same statement, just he started from n equal to 5. So what first thing was not due to Margulis. It was earlier. I think it was by Cassels and Swinnerton Dyer. And it's very often also attributed to Raghunathan. And it's from middle of 70s. The translation of the problem to the language of homogeneous flow. So the observation number 1 that one should make in this context is the following, that if you take M, which is a matrix in SL2R, such that Q of X can be seen as lambda Q0 XM, where Q0 is some very concrete quadratic form x1, x2. So what we do? We say that there exists a matrix in SL2R such that you can put your form in a kind of a canonic way if you make a substitution of the coordinates. And this lambda is some non-zero coefficient. And x1, x2 here we treat as a row vector. Ну, это просто, вы можете привести, форма у нас неопределенная, поэтому вы можете ее привести к каноническому виду заменами соответствующих переменных. Now, where is the flow? Here. So, observation 2. Is the fact that you can consider Q0 of x phi t as a Q0 of x for any phi t that looks like ET 0, 0, E minus t. You probably remember this matrix. It's very similar with the matrix of the geodesic flow, just we would divide it T over 2, but still it's very similar. So you can notice that Q0 does not change when we apply phi t. So now you may restate the things that you need, you now need to show the fact that for any positive epsilon, and there exists T, which is also positive, such that Z square M Ft contains a non-zero vector Y such that Q0 of Y is below epsilon. And the very last observations that I would like to mention in this context, once again, I'm not proving today anything, I'm just kind of advertising. So the very last observation for today, so observation 3, is that what we mentioned above, it holds if the orbit Z2 MFT, which is gamma MFT T in R, is dense. And actually, if you would try to repeat the proof for n equal to 2, you will be able to make this first step and even the second step, and everything will break only on the third step. So there is no proof. I will give it as a topic for the oral presentation for one of you to study how to apply the theorems from homogeneous dynamics to prove Oppenheim conjecture. But you probably already see that some statement that looks as a number theory statement in reality goes to the homogeneous space with a flow in it. So the very last thing I would like to say today is about two more possible applications that became very fashionable in the last years. First are quantitative versions of the Oppenheim conjecture. I will just state theorems. I will not prove anything. So Margulis in reality proved a stronger statement. He showed that Q of Zn, when n is greater than 3, is R. Apart from being dense, what can we say about the distribution of values of Q? So now we know that it's dense, so the closure of this set is R. And now we would like to know how is it distributed, more or less in the same style as we asked ourselves when we proved this Weil statement, yes, at the very beginning, how the numbers are distributed. And so there is a theorem by several brilliant mathematicians, Alex Eskin, Margulis, and Moses. And it was published in Annals of Mathematics in '98. And these guys showed that if Q is irrational and indefinite, P is greater than 3 and A is smaller than B, whatever two numbers, then we can count the following limit. On the top level, we will count all the integers in Zn such that they do not exceed T, and the Q of M is between A and B. Lim is under T. And here we count the volume of all the real numbers with the same property. And so this limit is equal to 1. And the key ingredient of the proof of both theorems is in reality the theorem proved by Marina Ratner in 1991 So this theorem really relies on her statement, and Margulis' theorem uses the construction, which is a particular case of Ratner's theorem. And so the goal of our course in this part is to arrive to the understanding of the Ratner's theorem. So this is just to let you kind of familiar with what people will currently do in this math, because okay, Margulis is still active mathematician, but Alex Eskin is very active mathematician. He's the one who, I think maybe 2 years ago, he won this breakthrough prize. And he does not, Margulis won his Fields Medal because of this Oppenheim conjecture proof in particular. It was mentioned by Fields Committee. And Alex does not have a Fields Medal, but his joint result with Mariam Merzakani were one of the two things that were mentioned by the committee for the reason why she has her Fields Medal. And the second thing is what Sergei Konstantinovich explained a week ago. So she won it for two contributions. One of these geodesic results that Sergei Konstantinovich explained, and one for her joint work with Alex Eskin. And so just to give you the idea what kind of modern mathematicians do. And the very, very last thing is not related to all this business at all, is the fact that people were able to apply homogeneous dynamics to so-called quantum chaos. So they study some kind of billiard classical mechanics systems, and then they switch from mechanics to quantum mechanics. So they provide a quantum analogy with the wave functions and Schrödinger functions, and they consider these systems and ask when they are chaotic and where they are not chaotic, and so on. And in this context, another Fields medalist who contributed very serious was Linda Strauss, who published the paper in Annals of Mathematics in 2006. And Anantaram, who also has a paper in Annals from 2008. So what they did morally, they took a hyperbolic billiard, hyperbolic exactly in a sense that we already understand due to our study of the geodesic flow. So it's some Anosov system. And then they provided a quantum version of it. So they wrote the Laplacian operator, and they asked what about some possible limits of the sequence of probability measures for this quantum version of the hyperbolic billiard. Can they say something? And what Lindenstrauss showed, apparently, under some conditions, he showed that the quantum billiard should be uniquely ergodic. And what Atalantarama showed is that under certain conditions, the Kolmogorov-Sinai entropy can be computed for this quantum limit, and she estimated this. So for a standard billiards, a normal one, not quantum one, for instance, for billiards in polygons, we also have typically, at least for rational polygon, we do have unique ergodicity, but entropy is always zero. So the quantization changes everything. And you see that the problems that look very, very far away from each other, apparently both use some applications that come from the homogeneous dynamics. And I think it's a good moment to stop here. The next lecture will be more regular. I will already start to build the way how we will formalize and prove some things that will allow us to finish with the Ratner theorem at the very end. Okay, thank you for your attention. See you next week.